We are starting our unit here on chemical reactions, and a lot of these take place in solution. So we're dealing really with two chapters in the Brown-LeMay textbook, mostly chapter 4, a little bit of chapter 13 mixed in. And we're going to start off refreshing ourselves on some things about solutions because so many of these reactions do occur in solutions. And the most common and the most important types of solutions are one with water as our solvent. We'll review some of these words here. But we've got a couple properties of water here. We see specific heat, vaporization, cohesive and adhesive forces. Those are all the technical terms or all the different chemistry ways of saying that water molecules stick to other water molecules very well. It sticks to itself, and it really sticks to a lot of other things very well. And that's because of intermolecular forces, and I really emphasize the inter part of that because there are inter and intramolecular forces when we're talking about things between molecules or things within a molecule. That's something we'll get a lot into in second and third trimester, entire tests and units dealing with that. But it's something that's important right now. So we're not talking about this bond or this bond. We're talking about why one water molecule sticks to another water molecule. And it all comes down to what we're talking about here is that those bonds are polar covalent. There's a difference in electronegativity, so a difference in attraction for the electrons. So this line right here is showing 2 electrons, and because oxygen has a higher electronegativity, that set of electrons, instead of being shared equally, really spends a lot of time down here and much less time up there. So we're not talking about these electrons here, this set of dots that I'm circling or this other set of dots. We're still talking about these shared electrons, and they are being pulled in one direction. They're being pulled towards oxygen, they're being pulled towards oxygen, and that makes the molecule as a whole polar. And we indicate that it has a charge by using this Greek letter delta. And you'll see that a lot, and that may be something that you have to add to a drawing to show which side's partially positive, which side's partially negative. So we've got our partial positive, partial negative. So that means it's not like a +1 like a proton or a -1 an electron, but it's a smaller charge than that. And with water, it's going to be very important to know the oxygen's the negative end, this end, the hydrogen end's the positive, and a lot of times like these down here, so I'm going to jump down to these smaller waters, we think of this as Mickey Mouse. So we've got the face, we've got the ears, the hydrogen part's the positive, the face, the chin, the head, whatever you want to call it's the negative. So remember that. That is or has been on multiple AP tests in a row a way to earn points. So just some things to refresh ourselves there with water. So the reasons water is so important, not just for people, but for molecules, is that it hydrates things. So we see hydration there. We've got these positive and negative parts of water. They attract positive and negative things. So this first picture here on the left, I'm circling it, is any ionic compound, but maybe this is sodium chloride, very common, NaCl. So we've got our positive cations. We know that cations are positive, and we've got our negative anions here in that repeating crystal lattice pattern. We've got positive to negative, and these ions actually have a full +1 or -1 charge, unlike the deltas we were seeing, because they have either gained or lost an electron. And it's the positives and negatives that hold any ionic compound together. Well, because there's partial positives and partial negatives, and we're going to look at this little water right here with its positives and negatives, it's attracted to the positives and negatives in that ionic compound. So we see as these waters get close, circling it right there, the ears, the hydrogens, the partial positives are coming close to that negative. Here, the partial negatives are coming close to that positive. We have attraction, and that process is hydration. When there's enough attraction here, what happens is the attraction between the water and the ion can overcome the attraction between these two ions. And we see that as we go over here to the right. We have a hydrated anion, we have a hydrated cation. There are a lot of attractions here. In this picture, it's just two-dimensional, but this chloride, this anion, has 6 water molecules around it. This cation has 6 water molecules around it. So there's a lot of new attractions that are made. Once again, I want to re-emphasize it's important to know the negative and the positive and which part of the water is negative. That is the oxygen part. That's the one in the middle. That's the head of the Mickey Mouse. Which part is positive? That's Mickey Mouse's ears. So that if you have to do a drawing like this, and it was on the 2014 test, it was on the 2015 test, it was on the practice exam given out by the College Board, there was a drawing like this. So I'm even going to zoom in on these a little bit. So we've got our anion, whoa, kind of around there. So we've got our Mickey Mouses, and this was described to me by another teacher as a Mickey Mouse playing poker situation. So we've got our poker table, we've got, all of our ions around it, and not randomly, we've got all of the ears next to the negative, or, change my, there, all of the heads or the chins or whatever you want to call them by the cation. Very important. Draw that. Think about that. When you are hearing about hydration, when you are looking at ionic compounds, think about what's negative. Think about what's positive. That is important. That is something to know. So as this is happening, we've got a couple different things occurring, and that's as we get down to this solubility. I think we're a little crooked. Try to straighten that up. We've got an attraction, as I said before, between the cation and the anion. So we've got an attraction right there, an attraction right here, an attraction right here. This chloride is surrounded by sodiums. This sodium's surrounded by chlorides, and they're attracted very strongly. Opposites attract. But once we get over here, it's strong enough to break it apart. That's because, if we were talking about sodium chloride, it is soluble. But if this same drawing were silver chloride, there wouldn't be a lot of difference. We'd still have a +1 and we'd have a -1, but it would be classified as insoluble because we have two opposing things happening. We've got our sodium to chloride or our silver to chloride, and that is competing with the hydration process, the water attracting the chloride and the water attracting whatever our cation is. If the attraction between water and your ions here is stronger than this attraction, sodium to chloride, it breaks apart, it's soluble. But if we have a really high attraction here, then these attractions, although they do exist, are not strong enough to pull it apart. We're also dealing with some different things. We're dealing with energy, we're dealing with entropy, some things that we'll come back to when we're talking about thermodynamics. But there's a lot of different forces here, but a key idea is attractions, positive to negative, partial positive to partial negative, and really understanding what all that does for us. So then as we scroll down here, I said partial positive to partial negative, and that was important because it doesn't have to be an ionic compound. Water can dissolve anything that has positive parts and negative parts, so it can dissolve things that are polar. So underlining polar right here. From our definition up at the top, we remember that polar means an unequal distribution of charge. So we have some sort of sharing of electrons that isn't happening equally. In water, it's the hydrogen to the oxygen. Sorry, thought I had my highlighter there. It's the hydrogen to the oxygen. In these examples, alcohols and sugars, right here in this, it's a hydrogen to oxygen, but it doesn't have to be those two atoms or those two elements. It can be any two elements that are sharing electrons but sharing them unequally. So here, partial positive, partial negative. We know water has that same partial positive and negative, so here our partial positive attracts our partial negative. We have attractions, hydration attractions, just like with the sodium chloride and the water. So polar here, they dissolve. Like dissolves like is the memory device we use in Chem 1. It's a great guideline. You use that to remember. You use that on multiple choice. You use that as a starting point for a free response question. But this is not a complete explanation. This does not say why it happens. It just helps you to remember what happens. So you like dissolves like means polar dissolves polar. Charges dissolve charges. Nonpolar dissolves nonpolar. So when we have those types of compounds, we know what to do. As we go on with the rest of this video, we're talking about things that are dissolved, things that have made those attractions. So all of that's done, all of that's taken for granted, and we're kind of understanding there are those attractions. Go to the next page, we're talking about things that are solutions, and specifically aqueous solutions. So some refreshers here. A solution needs to be homogeneous. That is the definition of that. The parts of it are the solute and the solvent. The solute, what gets dissolved. The solvent is what it dissolves in. And then we can have a heterogeneous mixture as well. It wouldn't be a solution. And it could be a colloid or a suspension, depending how big the particles are. As we started off talking with water, we're talking water here. Again, if we know the solvent's water, it's aqueous. That's going to happen so often that we almost assume that unless we're told something different. So when we are in aqueous solution, there's a lot of different properties or a lot of different things that we can know or want to know. And one is the idea that we can have something that is an electrolyte. So that would be an aqueous solution that can conduct an electrical current. The conducting of electricity is the movement of charge. So when something conducts, it's conducting because charge is allowed to move. We're going to kind of define a couple different degrees of electrolytes here in terms of does it happen a lot, a little, or not at all. But it's what we're thinking about is does it allow charge to move? And we'll describe that a little bit later here. But a strong electrolyte, something that strongly allows charge to move. The things that are strong electrolytes are strong acids, strong bases. That's where this all kind of comes together. We've got strong acids and strong bases. It's not just any acid that's dangerous or any base that's dangerous. It goes back to the fact that they are strong electrolytes. And then any ionic compound, that's what a salt is, that dissolves is considered a strong electrolyte. So we have three examples here. We've got barium chloride, so that'd be what this picture is showing, the positive bariums, the negative chlorides. It spreads out in the water, and we could show that the hydration. We could put our water molecules around it with the negative parts next to the barium. That would be the oxygens, the hydrogen ends, the ears next to the chlorides, and that would show its hydration here. But what we're focusing on here is the fact that it breaks apart. We don't have any bariums that are still stuck to chlorides. All of the bariums are ions, all of the chlorides are ions. When we put HCl, a strong acid, into water, we don't have HCl molecules. We have H's and Cl's. When we put NaOH, a strong base, into water, we don't have Na's and O's and H's or NaOH's. We've got Na plus ions. We've got OH minus ions. In all three cases, it completely broke into its ions. That's what completely dissociate means. So the electricity is flowing here because those ions are able to move around. They're not stuck to each other as a solid or stuck to each other as a gas or a liquid. Down at the bottom here, they're moving throughout the liquid. The electricity is flowing because these particles are moving and allowing that charge to flow with them. So it happens whenever we have an ionic compound dissolved in solution, an aqueous solution. If we took barium chloride or sodium chloride and melted it, so not dissolving it but heating it up thousands of degrees and turning it into a liquid, it would dissolve. Or this happens in solid metals because the electrons can move around. So when I said strong electrolytes and strong acids and bases, I mentioned that it wasn't just any acid or any base, there are specific ones that do this. It's not necessarily just the ones that are dangerous. It's not just the ones that have a molarity above a certain value. This is an intensive property. This is certain things do this in certain ways. So you have to memorize these. The acids are hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. So there's not any pattern really to follow there because there's some halogens but not all of them. There's some polyatomics but not all of them. You need to know these. Memorize them. Start studying them now. Know them when we get to the acid-base unit. Know them by May, because if you don't know them, you will regret it, because you need to know these are strong. These completely dissociate. The strong bases, there is a pattern. Anything in column 1 or 2 that's bonded to the hydroxide ion is strong. So right here we had sodium hydroxide, but we could have potassium hydroxide, calcium hydroxide, barium hydroxide. Any of those, when they dissolve, they completely break up, whether it's 0.1 molar or 10 molar. For HCl, whether it's 0.001 molar or whether it's 1 molar, it completely breaks into its ions. We memorize these because there's a small list of them. There is not a list of things that don't do this. The list of things that don't do this is everything else. So the difference here is completely or incomplete dissociation. They do not completely dissociate, meaning only about 5 to 10% of them actually break into parts. So we're going to look at this picture, the weak electrolyte versus the strong electrolyte. So this would be something like hydrochloric acid. There's no molecules that are still bonded together. The H's and the Cl's are separated. They're completely hydrated. If this were hydrofluoric acid, and it uses that as an example right there, what we would have would be this is HF. It's still bonded together. This HF is still bonded together. Then we have one H and one F that's by itself. Very little of it has ionized. A lot of it's still together. And because these don't have charges, these cannot conduct electricity. This positive, this negative can, but this molecule and this molecule can't. So here I have 2 things that can conduct electricity. Here I have 6. This can conduct electricity very well, very strongly. This, because there's fewer charged things, can conduct, but conducts weakly. Non-electrolytes are things that do dissolve, like ethanol, like sugar, but don't have ions. So we've got sugars, alcohols, antifreeze, starch, lots of things there. We're talking about polar things. They dissolve, but look at this. There's no positive, there's no negative. We only have partial positives and partial negatives, no ions, no charges, so there's no conducting of electricity. This is very important to know how to draw, especially when we get into these strongs and these weaks here. You will see pictures like this on quizzes, definitely on tests, and definitely on the AP exam somewhere. It appears a lot in multiple choice when we're talking about strong and weak acids, the difference between them. So if we look right up here again, it says only 5 to 10% dissociation, which meant if I were going to draw 10 molecules of this, if only 5 to 10, it should be 1 to 5% dissociated. Out of 10 molecules, fewer than one of them, or at most one of them, would have broken apart. So we would have had a bunch of stuff still stuck together. Barely any ions. If it's strong, I draw 10 molecules, all of them are broken apart. So this is something we will practice, but it's not something that we're going to be doing every single day over and over together. It's something you need to think about also on your own. So kind of the last thing we're going to talk about here is more of a chapter 13 topic. It's refreshing ourselves on saturation. So we've got all these solutions. Some stuff is dissolved. Maybe it's molecules, maybe it's ions, maybe it's a mixture of them. But there's a limit a lot of times to how much can dissolve. If you're dumping sugar into water, you can dump and dump and dump and dump it in, and at a certain point it's just going to pile up on the bottom. So this is refreshing ourselves on the 3 different degrees of saturation: saturated, unsaturated, supersaturated. And saturated is right when we have that maximum amount. No more can dissolve. We dumped in sugar, we dumped in, we're stirring it, it all dissolved. But if I added any more, it wouldn't. If the solution were unsaturated, I could add more and it'd keep dissolving. We have less than the maximum amount. Supersaturated really isn't worth our time here. It's actually kind of a fun thing. Go Google YouTube videos of supersaturated solutions, but it's not something that's really practical for our purposes. It's something where you force more to dissolve than really should be able to dissolve. You won't have to apply that definition. You probably won't ever have to explain how it can happen. Just know that it does exist. Saturated and unsaturated are the keys here. We can affect the degree of saturation by changing the temperature. Sometimes when it's hotter, more dissolved, sometimes less, depending on the solute. If we have a gas dissolved in a liquid, gaseous solute, pressure affects it. And as we get to gases, we'll remind ourselves of that. But those can change how much could dissolve. A potentially easy multiple choice question to either get or miss would be about how do you know if something's saturated or unsaturated, and it really goes back to the explanation I've already done here. If we added a little bit more, what would happen? We call that little bit more a seed crystal, an additional grain of our solute. If we add a little bit more and it dissolves, that's because more can dissolve. It was unsaturated. If we add a little bit more and it didn't dissolve, it just sinks to the bottom and nothing exciting happens, that's because we already dissolved as much. If we add more and we see a significant amount crystallize, that means that not only was that crystal not able to dissolve, but a lot of the stuff that was dissolved shouldn't have been dissolved. That's the sign that it's supersaturated. So this first video was just kind of a refresher on what solutions are, some key terms, some things to think about in terms of pictures and in terms of drawings. And as we go on, we'll get into the calculations, the concepts, and the applications of these things.